So welcome to the 9th lecture in the webinar series of INAE Chennai chapter. So for today's lecture, we have a very distinguished academic and speaker, Professor Sunil Sarangi, who is also my very good friend. And he will be talking on the topic of liquid green hydrogen technology and applications. So I'll just give a brief introduction of Professor Sarangi. Professor Sunil Sarangi is a fellow of the National Academy of Engineering, and he served as professor of cryogenic engineering at IIT Kharagpur. At IIT Kharagpur, he set up laboratories for study of cryogenic heat exchanges, compression and expansion machines, and computer-aided process design. Several of his doctoral students are holding senior faculty and scientific positions in leading institutes of India, NIT Roorkela, IITs at Kharagpur, Madras, Roorkee, Dhanbad, and as well as in ISRO and BARC. In recognition of his contribution to cryogenic engineering education, the Indian National Academy of Engineering has awarded the Outstanding Teacher Award for the year 2016. The Indian Cryogenics Council has also honored him with Lifetime Achievement Award in 2017. Professor Sarangi has also served as the director of NIT Roorkela, and with his rich administrative acumen, he served 3 full terms during the period 2003 to 2016. Under his stewardship, the institute established itself as one of the leading centers of engineering education, including cryogenic engineering and vacuum technology and research in India, giving a place to the NIT system in international rankings, Times Higher Educational and QS World Rankings. During his tenure, he also helped the NIT system establish itself as a stable and organized system of institutions of higher learning and research, a significant jump from the exclusive undergraduate identity of the RECs. Professor Sarangi, after superannuation from IIT Kharagpur, lives in Bhubaneswar. He is engaged almost full-time as an academic advisor to the C.V. Raman Global University with a mission of making CGU Odisha a leading center of engineering education research in India. He is also associated with IIT Bhubaneswar as Professorial Fellow. So before you start your lecture, I will just say that you can talk for about 50 minutes and so on, and then we will leave about 10 minutes for question and answer session. I would ask Professor Nandita Dasgupta to moderate the question and answer session, and also at the end propose a vote of thanks. So Professor Sunil Sarangi, so you can start your lecture.
Okay, thank you, Professor Narayanan, for introducing me to an august audience. And right now I'm sharing the full screen and I cannot see my audience, and it's very uncomfortable for a professor, but I will try to live with it. So I will start with why this specific topic came to my mind. You can see there is a little tender news item in the papers, and there is another news item in similar lines, and there are several which came over the past couple, about a month or so. And you can see that this green hydrogen is a big thing, and so many news items, so many good things happening in the hands of the government and in the hands of large companies. And they say that the MNRE secretary has recently said that government is likely to come out with a mandate on the green hydrogen usage. It means green hydrogen, and of course we are going to talk about only a subset of green hydrogen, that is the liquid green hydrogen, is a big thing and going bigger every day. And here is a document which it's a very pleasant to read this. It has many authors, no unique author. It probably has 100 names in the authors list. And if we see, look at the contents, and Green Hydrogen Initiative for Research and Innovation in India, hydrogen production, hydrogen storage, hydrogen transport, then end use applications, and enabling the hydrogen framework. Okay. So let me very quickly, I just told you there have been many advertisement news items in the paper which triggered my interest in this green hydrogen. So these are the kind of news items which came. Government floats tender for 4.5 lakh ton green hydrogen, then India's first green hydrogen fueling station to start within 3 months in Leh, Ladakh, and they would have a bona fide green hydrogen fueling station out there, and 80 kg per day with a very pure hydrogen. Green hydrogen bid, another Indian companies are bidding in Germany for $1 billion tender, and so on. Then I can go to that mode, and you are able to see it. NTPC awards India's largest contract.
Yes, sir.
Okay. So you can see all kinds of good things happening in the country in big scale, and so many news items on the issue. So it's kind of appropriate that in the academy seminars we spend some time on it, and I think it will be useful. I draw attention of my audience to the specific document which is in the internet, and it says R&D roadmap for green hydrogen ecosystem in India. It's a government document from the Ministry of MNRE, and you can see the contents. It's really beautifully researched document. There is a hydrogen production, hydrogen storage, hydrogen transport, hydrogen end use applications, and enabling hydrogen framework. Not liquid green hydrogen, but hydrogen per se. So as we said that we were in this R&D roadmap. Uh, well, there are only news items which I read out, and comes R&D roadmap, and said this is a beautiful document, and here are the contents page: hydrogen production, storage, transport. I'm specifically drawing attention of my audience to this document. You can get on the internet, and this one, the benefit is all the government policies and lots of information, lot of science and technology to learn from this. Okay, so now let's come back to our subject, liquid green hydrogen. Basically it has three keywords: hydrogen, green, and liquid. It's in the reverse order from more general to less general. So if we go to this, I am not extremely satisfied of what I have prepared, but we'll proceed in that order. Let's see. If you see the hydrogen gas, all these are common chemistry knowledge. Just a little bit of reminding people on it, so that you have an idea of where we are standing. The gas constant, of course, very simple. That is the universal constant, gas constant, divided by 2. That's per atom. So that's 8.3 moles per Kelvin. The molar mass is 2, and critical temperature is 33 Kelvin, and critical pressure is 12 bar, 13 bar, and critical density is 15 kilomoles per meter cube. It's a difficult unit, but I'll tell you other information. Triple point is 13 Kelvin. So the hydrogen becomes solid at 14 Kelvin. The boiling point is 20 Kelvin. 20.2 Kelvin is the liquid vapor transition, and the liquid solid transition is 14 Kelvin. So 13.96 is the triple point, and triple point pressure, of course, is 0.07 bar, some 73 millibar, and density in the liquid state is 38 kilomoles per meter cube. It's difficult. It's 70 grams per liter. You just compare. I'll give you other numbers. Water, of course, is 1 kilogram, 1000 grams per liter. Liquid nitrogen is 810 grams per liter. Liquid oxygen is 1142 grams per liter. In comparison, helium is 130, liquid helium, and liquid hydrogen is only 70 grams per liter. It's very light, That means good numbers, which is so much per kg, do not mean much because that is so much for a lot of volume. So therefore, when it comes down to so much any property per liter basis, then it becomes unattractive. When it becomes per kg basis, it becomes very attractive. But in spite of that, it has a lot of potential. And just talking of science, the property, here is a graph. It gives density as a function of temperature. It is very important. The reason is the liquid density you can see is 70 grams per liter, right on top of this line. 70 grams per liter is the liquid density. And the gas density at ambient pressures is virtually nothing. But when you come to the boiling point, minus 253 degrees C, or just 20 Kelvin, you find there is a sudden rise from virtual nothing to 70 grams per liter, because that is the liquid state. So this is the liquid vapor transition at atmospheric pressure. And then as you increase the pressure, 10 bar, 50 bar, 100 bar, 300 bar, and 1000 bar, these are important because today's hydrogen gas containers, which are being commercially utilized to carry hydrogen fuel in cars, buses, trains, or any other application where hydrogen is being used, particularly in the mobile sector of the economy, there are two standards: 350 bar and 700 bar, means 35 megapascals and 70 megapascal. And at room temp 0 degree C or room temperature, you probably require something like 1500 um, this you know 15, this is 1000 bar, some 15,000 bar pressure will give you the liquid density. So on the gas phase, it's very difficult to get liquid density simply by compressing. But at 350 or 700 bar and room temperature, you are able to get half the gas density. 700 bar, at room temperature, you get approximately 40 grams per liter. Liquid is 70 grams per liter. 700 bar, 40 grams per liter. 350 bar, something like 24 grams per liter. I am repeating these numbers basically to convince my audience that at extremely high pressures, but realizable high pressures, they are being used today by these fiber reinforced plastic tubing, I mean, cylinders, and 350 bar and 700 bar have been realized and being used commercially, means they have been taken to that much of reliability. The same information, another plot, it has same stuff. You can see it has gone up to 880 bar, 880 bar and 300 Kelvin, and you have about 45 grams per liter. But you see something at this side on the top left corner. On the top left corner, you see 70 grams per liter is the density of the liquid. But if we take high pressure gas and gas or liquid, in supercritical region, the gas liquid distinction vaporizes, vanishes. So if you take high pressure fluid at 250 bar, 300, 350, 500 bar, and cool it not to 20 Kelvin, but let us say 77 Kelvin, and I have like 800, 900 atmosphere, I'm able to get a density higher than 70 grams per liter. And in fact, this is called compressed, cryo-compressed hydrogen. This is liquid hydrogen. Cryo-compressed hydrogen is hydrogen gas at extremely high pressure in our imagination, and several hundred bar, and cooled to 60 Kelvin, 50, 40 Kelvin, they probably can be done using not liquid helium kind of machinery, but more benign machinery. And these are also used so that it is possible to get densities beyond 70 up to 80, 90 grams per liter. But in that range, you cannot do much better than that. So once you are there, few more things here. There is a gravimetric energy density kilowatt hour. This is our electrical 1 unit per kg. That's the unit. And volumetric energy density is here, kilowatt hour per liter, and this is kilowatt hour per kg. And you can see diesel, gasoline, they have high energy density in the order of 10 uh, in per kg basis, and also a lot in per liter basis, because these are dense fluids. But less dense fluids are liquid methane, which is our LNG, liquefied natural gas. LNG, liquefied natural gas, we have this kind of energy density per liter basis. Per kg, better or slightly better because it's reasonably light. Methane gas are 250 bar. And here comes hydrogen, very large number on per kg basis, but per liter basis, the lowest among these. So we must be talking in that context. So we are talking of hydrogen as a fuel or as a product for as a chemical feedstock to companies, or even to make as a thing to be burnt in, like in a steel plant or in a power plant to produce electricity. I'm talking of three types of application. One is as a fuel in a power plant to produce electricity, or as a fuel in steel making to obviously reduce iron oxide ores, or as a automobile fuel where it is used either as a internal combustion engine or in a fuel cell where hydrogen and air, oxygen from the air, they react and produce electricity directly. And the fuel cell efficiency is not limited by Carnot efficiency. These are applications. I'm talking of hydrogen applications. We are talking of it being used either as a stationary fuel in, or as a chemical feedstock in large plants, or it is used as a fuel in power plants produce electricity, or as a fuel in a steel plant in very big scale to produce iron from iron ore, and so on, or in the mobile sector of the economy to fly airplanes, to drive trains, buses, cars, all that. We'll take a look at these applications a little later. But the first thing that comes people's mind, is it safe? Is hydrogen safe? In fact, this is a international prejudice. Hydrogen is actually very safe, and agencies like NASA have taken a lot of pains to do experiments, and the US military, they have taken a lot of pains only to establish that hydrogen is safer than anything we are used to. I have two pictures here. You just see. This is a very famous picture. It is the Hindenburg disaster. Of course, there is a Hindenburg Adani type of disaster, but this is the other one, happened in 1939 or so. This was a spaceship or airship traveling between Germany and USA, and there were two, the Graf Zeppelin and the Hindenburg. There were several Graf Zeppelins, and cumulative probably did for about 2 million kilometers traveling between USA and Germany in a lighter than air balloon, and of course there would be a passenger compartment. This Hindenburg was similar to Graf Zeppelin, but they did some shortcut. There were certain steps taken to either make it cheaper or lighter, have more people or whatever, and it collapsed in New Jersey, USA, and caught fire, and everybody got cooked. So that gave a lot of impression world over that hydrogen is unsafe fuel, unsafe product, and this is true. But look at this thing which was done by Department of Energy USA, and they said there are two cars. One is having gasoline, petrol, other is having hydrogen, and this of course had a hydrogen cylinder, and there was fire. When there was a fire in the hydrogen, this is how the hydrogen behaves. It goes up and it catches fire almost immediately and keeps going up away from the car. And that's the story after 3 seconds. And there is a little fire here. And this fire in 1 minute is still burning, and this fire has become much bigger and has engulfed the car. And after 90 seconds, this is almost extinguished. The passengers are safe. The car is cool. That's because the hydrogen catches fire immediately. It expands in the atmosphere very quickly and rises up. And although it catches fire, it doesn't stay for long enough time and doesn't spread from doesn't go down to engulf the car the way the fuel does in petrol or diesel. And that's the end product. The hydrogen car is safe and so on. In 1984, I had the opportunity of spending a year with the Los Alamos National Laboratory in USA, and that specific group, apart from other things, was actually running a hydrogen filling station. There are 7 cars. They ran on liquid hydrogen. There was a container at the back, and they were given to lab employees, properly insured and all. And they ran it for a couple of years, and there were 2 accidents in between. One car overturned, but there was nothing negative happened in the process. So that community was very convinced that hydrogen is safe. In fact, liquid hydrogen containers are plying on the highways from 1960s onwards, particularly in connection with the space program. So in our country also, these liquid hydrogen truck, it's made in Nagarcoil, and then that's where the liquefier is. And then from there, that's Mandragiri in Nagarcoil district. And from there, it goes on the road to Sririkota, and it's traveling. And in USA, that has been happening for from Apollo days onwards. And there has not been several million kilometers have been logged, and there has not been a single accident. Accidents have been there, no death resulting from the accidents. So when we go to the about liquid green hydrogen, here is a picture that says a few things about it, on resources, on production, on storage and transport, and utilization. So ignore the scope of this review. This is taken from a certain document which reviewed things of that nature. And this is the cryogenics part basically. But if you look at it, if you can read it, so let's see from the resources. There is coal, natural gas, biomass, waste, nuclear, and solar and wind. You can see this is the green side. The right side is the green side. The product is green hydrogen because it does not contribute to carbon footprint. But by cracking coal or natural gas or biomass and so on, in fact, biomass is sometimes considered green because the carbon dioxide in the atmosphere is coming back to the atmosphere without adding anything to it. So biomass is a questionable thing. Sometimes it's on the green side and sometimes it's not in the green side. Then this all these, then the production methods are there. There are different methods how this coal, natural gas, or biomass can be converted to hydrogen, and that is actually called gray hydrogen. If you drop this line, this carbon capture, use, and storage, if you come across a phrase called gray hydrogen, that's actually hydrogen produced from coal, natural gas, or biomass, or any other fossil fuel, or any fuel with a big carbon footprint, if that is called a gray hydrogen. And then if somehow, because it is being produced not in a distributed manner like the whole country, but in a factory, and if the flue gas is captured and the carbon is captured and immobilized and made into some other chemicals and not allowed to go into the atmosphere, that hydrogen would be called a blue hydrogen. Basically, it's a gray hydrogen, blue hydrogen is the same production process. In the gray hydrogen, we do nothing with the carbon dioxide which is produced. But in the blue hydrogen, when we produce what we name as blue hydrogen, we use the carbon, we immobilize it, we capture it, and the hydrogen goes one way and any other waste gases go the other way. But let's focus on the green hydrogen. The green hydrogen has no carbon footprint. So obviously its water goes into an electrolyzer and then we have electricity, and that has to be a green electricity. If you are electrolyzing using electricity which came from a coal-fired power plant, obviously that's not green electricity, and if that's not green electricity, that's not green hydrogen. So we are assuming we have solar and wind power, or we have nuclear power, which may have its other repercussions, but it is certainly green from carbon point of view. And with these, we produce what is called the green hydrogen. Now comes the storage and transportation. In storage transportation front, that's where this liquid hydrogen comes in. This box is for that. Then you can have a compressed gaseous hydrogen. You can have compressed gaseous hydrogen. I have to make it silent. You can have compressed gaseous hydrogen. Then there is liquid hydrogen. Then there is ammonia. Not only ammonia, there are other liquid organic hydrogen carriers like methane or like formaldehyde and so on, and with another carbon atom somewhere there. And then there is, of course, uh, hydrogen hydrates and other kinds of solids. And so the hydrogen has to be transported. One of these compressed things, either you can put it in a pipeline or take it to a road tanker or rail or shipping or whatever. All these are possible with compressed gaseous hydrogen, and then it goes to the application point. And normally, as we said, if gaseous hydrogen in a pipeline, it can be at low pressure, but all other ones, it has to be at a high pressure. And we are talking of minimum pressure of 350 bar, and modern trained, after the technology of the container has been set up, it's like 700 bar. Liquid, of course, here, of course, we are talking of densities in the range of 24 grams per liter at 350 and 40 grams per liter at 700 bar. Liquid is 70 grams per liter. Then this ammonia, NH3, you can understand that if we somehow create a chemical, suppose we have hydrogen, then we burn with ammonia, and we come back to NH3, and there is a lot of hydrogen in there, some amount of ammonia, nitrogen, and then we transport that liquid ammonia, only mildly pressurized. Liquid ammonia can go in pipelines, in trucks, mostly in containers, goes to the destination, and again we crack it. Nitrogen goes its way, and the hydrogen goes to us as a fuel or as feedstock or whatever we want with it. And then, of course, just like ammonia liquid, there could be other organic carriers where carbon and hydrogen combine, create chemicals which are liquid state, and they can be carried in trucks. And then what is not conspicuous here, another way is the adsorption methods. That means particularly there are things like rare earth materials like lanthanum, dysprosium, things of that nature, and you make certain porous bodies, and hydrogen can be adsorbed on them and dissolved by mildly heating it. We are talking of temperatures in the range of 30 degrees to 80 degrees C. In that range, it can be adsorbed and dissolved, and a solid state carrying is also possible. So, and when it comes to utilization, we are talking of course, chemical feedstock. Then it can be aerospace, means rocketry. Then mobility applications, it's like automobiles, buses, cars, trains, and aeroplanes. Then energy plants and energy, what does it say? Storage, and then combined heat and power, and so on, so on. Anyway, you can use a fuel, that's not the issue, and hydrogen is very easy to burn. And then quickly let's go to, this is similar. It says fossil fuels and renewable sources, and here it puts biomass. In the other drawing, it put biomass under non-green, and here it's in the green stage, and from there it can for gasification, pyrolysis, And of course, if you have water splitting, it's electrolysis. And then electrolysis, we are not covering that, but a lot of research is going on to find out a very efficient way of splitting water. Uh, as I understand, it takes 3.84, something like 3.84 units, that is kilowatt hours of electricity per kilowatt per kg of hydrogen. And but current technology is like 10. So we are operating at about 40% efficiency in the electrolysis. That's where we are. Okay. So as we said, the similar kind of stuff, hydrogen product pathways, it goes from fossil fuels to renewable sources, and same mechanisms, you are coming to the same point. Here is something. It says the cost estimate, electrolysis of water, obviously rupees per kg of hydrogen. It's much more expensive than any of these other ones. And then why it is being considered? Because this does not have a carbon footprint. Whereas these, the cheaper ones have a lot of carbon footprint, little bit little bit less, and this is of course zero. That is why, although it's expensive, we must strive to make them cheaper and take them forward. And then if you this one is again similar. That means on the hydrogen production and storage. This is on storage. This is the hydrogen storage technologies. It may not be extremely readable, but basically it says there can be compressed cylinders or there can be liquid hydrogen. This is a cryo compressed. It says cryo compressed here. Means it's cold, low temperature, but not as low as 20 Kelvin. This is 20 Kelvin liquid, maybe slightly pressurized 5 bar, 7 bar, 3 bar. But this is at 200, 300, 500 bar, and again cooled to 40, 50 Kelvin. And thermodynamically, there is a big difference in 20 Kelvin and 40 Kelvin. And at high pressure, the density increases and the cooling cost goes down. So optimum could be somewhere at a different temperature and which can be produced. And this is of course straightforward compressed gas. It shows of course a traditional steel cylinder out here, but in reality these are composite cylinders with carbon fibers and stuff like that. Then there is adsorbed phase. These are all the solid state material based, where these are adsorbed phases, and then hydrogen may be carried and again heated for desorption. Here is a comparison of the different modes of carrying hydrogen. We have the metal hydrides here, and then the cryo compressed, and then there is this liquid organic hydrocarbons kind of stuff, and then of course there is a liquid hydrogen which has a zero operational pressure bar, means ambient pressure, and that's also ambient pressure, this liquid organic stuff. And what we find, the temperatures here is 20 Kelvin. The rest of them are at room temperature, except metal borohydrides. These are all research level stuff. They have not been commercialized. But a cryo compressed 40 to 80 Kelvin, and high pressure more like 300 bar. So these are the conditions. And then you can see the liquid is 6.4 megajoules per liter, and other ones are all comparable. It is not that these ones are recent research, they have not been commercialized, not proven, but the proven ones in chemical, it's a high amount of energy per liter, but then to bring it out of it, we probably create a carbon footprint in the process, pollution. So there are, thus we say that the gaseous transport, for transporting, these are the options. They can be gaseous transport, liquid transport, solid transport in adsorption in metal hydrides, and there is a chemical conversion, convert it to methanol or ammonia or synthetic natural gas, and then take it through pipelines or road tankers and redo the, reverse the chemical reaction, and so on. And these are the modes of transport. That's no big deal. So if you go forward, we'll go to a little bit of science. And why liquid hydrogen? It's a photo taken from a very nice article by Jacob Lichman, and he's from the, I think, Washington State University in USA. And the reason for liquid hydrogen is purity. Because it is 20 Kelvin, any impurity would be solidified. A straightforward, screen filter would remove all the other material. You can get very high purity hydrogen, particularly for space propulsion or for any other application where you want high purity. It can naturally come, and not much effort has to be put in to get this kind of purity. Power density, suppose there's a tanker truck, you can carry 4,000 kg, 4 tons of hydrogen, is a big truck. But the high pressure cylinder, you take only 750 kg. So transport cost. Power density, similarly in a hydrogen refueling station, you can put 4 megawatt at the rate of 4 megawatts. Means in a few minutes you can fill a vehicle. A truck can be filled in 5 minutes. But if there is a battery supercharger, at this rate it will take a long time, 40 times more. Safety, tankers plying in highways around the world since 1960, not a single death so far, which can be ascribed to liquid hydrogen. Availability is global. Wherever there is water, there is hydrogen, and you need water and electricity. And efficiency, I have told that 3.84 kilowatt hour per kg, but current technology, this is the maximum efficiency. Minimum number in kilowatt hour per kg, but this is the maximum efficiency. And but the current technology is more like 10 kilowatt per hour and likely to improve. In this context, well, this only pictorially represents whatever we discussed so far. These are the production and then carrying, the transportation and the utilization. And in this, there is a article, there is a book. A lot of things have changed obviously from 1992. This is a 1992 book by Walter Pesca. It's available e-copy also quite easily, and this is a reference. So in then of course there is other articles by Leachman, and there is another one by Leachman. He says somewhere, he has told here, there is too much reading, I don't have to spend your time. Basically he is kind of pleading that we don't put large hydrogen liquefiers. It is not necessarily more economical, more distributed, 5 tons per day capacity. Liquefiers are best because the tankers are 5 tons capacity. So you produce 1 tanker a day and it will serve a certain area in terms of automobile requirements and so on. This is a pictorial representation of what we all know. This is gaseous hydrogen, and there is a liquefier, and there is a storage, there is a distribution system, and then there are trucks which carry the liquid, and then you fill it up into automobiles or trains or airplanes or whatever, or even ships, and then put it into the application. And then let us go to the details, something which is closer to my heart. This is liquefaction and storage. Let's see. A small liquefier would look like this. You can see this is a evacuated container. This is Linde company of Germany, and there are other companies around the world, particularly in France and USA. L'air Liquide in France is a big company, and so Air Products and Chemicals in USA and others, Praxair. So they produce liquid hydrogen, and they have these liquefiers. And what is the method of liquefaction? We have a reasonably detailed analysis of that. We'll go into it, but this shows a typical liquefier looks like this. You can see all the valves and the plumbing and the controls and so on, so on. And this is like a large storage tank that also has different kind of controls, multiple valves, so that you can fill, you can drain without contaminating air. Any pipeline must first seal itself, must purge itself, and then only, so there will be self-sealing couplings, so that liquid hydrogen does not spill out, does not cause a fire danger, and does not cause air to solidify coming in contact with liquid hydrogen. So if we are talking of a container like this, that is a specification. This is one specification. There could be many. So it would operate at like 12 bar and would have a capacity of something like 26 tons of hydrogen at 70 uh, kg per meter cube, 70 grams per liter, and that's a lot of volume. And these are insulated, vacuum perlite, or super insulation or glass bubbles. What are these words? Cryogenic engineers are very familiar with the type of insulation. In fact, somebody once calculated and showed that if we take a reasonable size and reasonable quality liquid helium container and fill it up with coffee at 100 degrees C and seal it, keep it for 70 years, wake up and sip the coffee, it will be perfectly drinkable and taste very nice. Chemical change, no guarantee. So what I'm saying, we're talking about very high quality containers used in cryogenic practice. The insulation are not foam or whatever we normally use in air conditioning, but we are talking of very superior insulation. There are three things listed here. There is a substance called perlite. It's called exfoliated perlite. It is some aluminosilicate, something like calcium, strontium aluminosilicate, or some stuff like that. It's an aluminosilicate. It's available as a rock. You can see all this geological stuff. They have this ITE at the end. They make fine powder of it and then cook it at a high temperature. They expose it to very high temperature. This powder, the crystals which contain lot of water of crystallization, it escapes, and as a result it becomes like a porous body. It is similar to the kind of stuff at least we are used in eastern India in eating. It's called mudi. It's only rice grains which are cooked on sand in a earthen pot at high temperature, not no water in contact, so that it kind of blows up and becomes very very porous. And this perlite powder is looks like that only, and that they put in a in the annular space around the liquid hydrogen space. It's used for liquid oxygen because it's not organic, because it's a rock, aluminosilicate. So it's compatible with oxygen, it's compatible with nitrogen, compatible with hydrogen, argon, whatever. And then it's further evacuated, but it's a low quality evacuation, something less than, it's better than 100 micron pressure. So it's like, uh, so it's like a microbar pressure. So what we say that we are not talking of a perlite insulation. Large oxygen plants are actually insulated using perlite powder at atmospheric pressure, but this insulation is evacuated perlite, and it is a good quality insulation. But better than this is called super insulation. Super insulation is the annular spaces at high vacuum and like 10 to the power minus 6 millibar, and there are aluminized mylar reflectors, and that is how extremely good insulation is obtained, and acceptable boil off ratio, like you fill up a tank, it will last for 400 days, and then vertical, horizontal, and ASME section weight is fairly standard. So on. We are then containers like this, these are also double walled and perlite insulated or super insulated. And then of course this is photograph of a filling station. Then how do is liquefied? There are many slides out here which tell what are the methods of liquefaction. I'll just cover one or two because we are coming to the close of our timing pressure, and this is called the well-known linear cycle. This was used for air in around 1895 and so on. So it is there for more than 100 years. All you have a heavy compressor. For air, this pressure would be like 250 bar. 200 to 300 bar. But for hydrogen, the optimal pressure is 120 bar. We have between 100 and 120 bar from atmospheric pressure. Then there is a counterflow heat exchanger. It should be a smart heat exchanger. And there is a particular design which would hold such a high pressure and such low pressure at the other side. And then there is a orifice valve, just a valve, a Joule-Thomson expansion. And if we plot all these on a temperature entropy plot, it can be explained how the liquefaction actually happens. But this takes advantage of the Joule-Thomson effect and the non-ideality of the fluid at a temperature above atmospheric at a low temperature and high pressure. So this deviation from ideal gas behavior is responsible for this particular JT effect. And then of course there has to be an aftercooler and so on with this compressor, and then comes liquid. Very simple. In fact, the Mahendragiri helium hydrogen liquefier, which ISRO operates in Mahendragiri, Nagarkol district, and ships the liquid to Sriharikota, and which was responsible for lifting the rocket, moon rocket up yesterday, and that's all based upon this cycle, 120 bar, and you simply compress the hydrogen valve, as simple as that. But to improve the efficiency, things can be much more complicated. And then there is a pre-cooled with liquid nitrogen. It makes things a little cheaper because much of the cooling load is taken by liquid nitrogen, which is made in large companies, large containers. We buy liquid nitrogen. So much of the cooling job is done. It is 77 Kelvin. This is 20 Kelvin here, and so on. And then there are two level to double pressure stuff, and then double pressure with liquid nitrogen cooling. Then there are others with more, thermal engineers out here would be very unhappy with the irreversible cooling process of the Joule-Thomson expansion. They always want this is the refrigeration cycle with a compressor, condenser, evaporator. It doesn't work in cryogenics, but it can, not up to liquid hydrogen, but up to liquid nitrogen or LNG, etc., are done by cascading refrigerators. And there is, of course, the mixed refrigerant cycle where you combine things like propane and ethylene and methane and nitrogen and go forward and have multiple expanders. The gas goes one way, the liquid is re-expanded back to this, and all. This is called the MRC, mixed refrigerant cycle. And you cannot produce liquid hydrogen by MRC, by mixed refrigerant cycle only. MRC is a highly efficient cycle. So we do a MRC pre-cooling, take it to 80 Kelvin using a mixed refrigerant system, and then we use a Linde cycle, which we learn to get up to hydrogen. So there are stuff of that nature. Here is another cycle with a multiple heat exchanger and an expansion turbine. It's an isentropic device compared to this fellow, which is an isenthalpic device and irreversible. It's a reversible device. So we get much better thermal efficiency in liquefaction. So there are several types, and like that, you make it more complex. Larger plants make it more complicated, it will work. And then there is the Brayton cycle. This is the helium based cycle. It is compressor, expander, helium based, and hydrogen goes piggyback on top of it, and helium liquefies at 4 Kelvin. So it's purely in the gas phase, and hydrogen liquefies while the helium remains in the gas phase. There is another interesting physics happens is, I'm not going to spend much time on it, but it's something unique to hydrogen. And only in hydrogen, all nitrogen, oxygen, all of them have, all diatomic molecules have this, but they really don't affect, whatever. Some transition temperature is so low, they are not thing to be considered. But in case of hydrogen, you see it's a diatomic molecule. There are two protons. They have a proton spin. The spins can be parallel or anti-parallel. The irony is the anti-parallel is called para-hydrogen and the parallel is called ortho-hydrogen. These are two states of the hydrogen molecule. And normal hydrogen is divided, some para, some ortho. Normal hydrogen, again, it can be calculated by quantum mechanics very easily, elementary calculation. It says that 25% at room temperature would be para-hydrogen, 75% ortho-hydrogen. As you go to lower and lower temperature, you go below 150 Kelvin, and it becomes 100% para-hydrogen by the time it makes liquid. And this conversion is an exothermic process, and its latent heat, or the heat of conversion, is more than the latent heat of vaporization. For hydrogen, I think 447 kilojoules per kg is the latent heat of vaporization. For the orthopara conversion is 523 kilojoules per kg. So what happens is, and this happens slowly unless you use a catalyst. So they have some iron hydroxide catalyst or something. If during liquefaction you have the catalyst and the liquid is made to flow over the catalyst, this conversion happens while the liquefaction is taking place. Otherwise, you liquefy it, this conversion doesn't happen immediately, it happens slowly. You make liquid, fill up your container, go home in the night, come back in the morning and find all of it has vaporized, because the orthopara conversion heat is more than the latent heat. So it converts from ortho to para, produces heat and boils away. So that is what happens. And there is some other, okay, here is a graph which says where the losses are, something in the compressor, something in the expander, something in the heat exchanger. You can see the compressor is a big culprit, and so is the liquid nitrogen refrigerator, if it is a nitrogen cooled stuff. And here is another, we are coming to the almost to the end, just a few minutes more. And here there have been many reports of what kind of efficiency, and the green is the efficiency, and this is the work input. So long ago, Tapas Nandi was my student, and in early 1990 we produced a hydrogen, a liquefied hydrogen at Kharagpur, and that you can see used a huge amount of electricity and had a very low efficiency because it was Linde cycle operating at 120 bar. And of course we had bad heat exchanger and so on, whatever you can achieve in the institute. But when it comes to industries, today's this doesn't seem to be believable, because that comes below the theoretical requirement of energy. But you can see the ideal requirement is like 3.84 kilowatt hour per kg, and people are getting about 10 kilowatt hour per kg in industry. And then that is it. So you make larger plants, you can save on electricity, and so on. So in a 5 TPD plant, 5 tons per day, you are getting this kind of liquefaction cost. But you go to 100 tons per day, you are getting obviously less than half of it. This is something with magnetic refrigeration. I will skip that. And then of course I had shown you how liquid hydrogen is stored in a double walled container. You have the liquid hydrogen in a cylindrical container or a spherical container, and then there are multi-layer insulations, and there is extremely high vacuum, and even there are heat shields which are cooled by the evaporating gas, evaporating liquid, and so on, so on. So this is pretty normal for cryogenic systems. And then we have, here is an arrangement, it's quite smart. What says that there's a liquid hydrogen tank, and you attach a fuel cell to it. The hydrogen, whatever vaporizes, it goes to the fuel cell, produces electricity, and with that electricity you run a refrigerator, so that the cooling requirement or the heat input, much of it is consumed by this refrigerator. Whatever remains, that produces evaporation, and hence the tank, a large tank, would benefit from an associated fuel cell, because whatever hydrogen evaporates, that with that we operate the fuel cell, and then with that electricity operate a refrigerator and keep it surrounded, or whatever, some recondensing done by it, everything will be fine. So storage cost, similarly, compressed hydrogen, you can see that's little lower cost. Liquefaction is costlier than compressed hydrogen, That is why people are going to 350 or 700 bar, and metal hydrides. They were tried for a long time. In fact, BHU, there was Professor O.N. Srivastav did a lot of work on this in 1990s and so on, and was quite successful. But then, when the new technology came for making these carbon fiber based composites, which could sustain hundreds of atmosphere pressure at reasonable sizes, these metal hydrides have fallen out of favor. But then somebody may discover, in fact, the other day I read a paper, certain perovskite materials at extreme, very normal temperature, like between 30 degree and 60 degrees C, could absorb a lot of material, lot of hydrogen. And maybe discovery of new materials and new porous materials could make a difference and bring metal hydrides back. And so on. I just had these two slides. They are unrelated. My talk is over. And this shows that how hydrogen instead of coal can be used to produce iron and steel from iron ore. And there is a comparison between hydrogen plasma smelting reduction for steel making, for iron making, and conventional process in iron making. And of course, most of the benefit comes in environmental benefits, and the cost, of course, is higher for this. But it's a reasonable proposition, and very likely that a couple of decades down the line, much of our steel will be coming from hydrogen driven furnaces rather than the coal driven blast furnaces of today. Thank you, sir.
Thank you, Professor Sarangi. Thank you for a very informative, interesting, and exhaustive lecture on liquid green hydrogen, covering all aspects of production, safety, then application, storage, economy, and so on. So now I will ask Professor Nandita Dasgupta to take over and then sort of moderate the question answer sessions. So if there are questions,
thanks a lot to Professor Sarangi for a very informative lecture. In the interest of time, we can probably take just a couple of questions. So already there is a question by Vivek Kashyap.
Yeah, thank you. Thank you. This was really nice talk. I would like to ask two questions to the professor. The first is, currently the research is going on the hydrogen power paste, which is a combination of metal hydrides and esters. Could you please make a comparison for this kind of fuels, which is generally a paste form, to the conventional gasoline fuels for the motorbike application in order to increase their mileage? And the second question is, what could be the possible way to reduce the production cost of hydrogen fuel? Whether it could be in the form of gaseous form or metal hydride form or in the liquid form, but how to reduce the production cost? Yeah, these are the two questions. Thank you.
Okay. Now, regarding the first question, it is very, very focused on a specific product. I have no first-hand or even third-hand knowledge on the subject, so I will not venture. But my general impression is that metal hydride, these adsorption things are at a low key at the moment, and the biggest commercial investments are happening in the high pressure gas storage, and liquid storage or transport is being used only for bulk transportation. Like even I saw the picture of a train, small train in Germany running on hydrogen, actually commercially plying on the regular route, but it had on the roof an array of high pressure cylinders, not steel cylinders, but the composite cylinders on the roof rather than liquid, whereas a application like a rail would always benefit from the liquid. But liquid people are little unhappy about because it vaporizes when the system is idle, and unless something is running continuously, they don't go for liquid, but they go for it in city bus service where the bus can return to the depot at a fixed hours to get it refilled, and they're running every day, and so on, and that could be better than compressed gas. When it comes down to absorption, even in the paste form and so on, these are research innovations which are happening, and I believe the world is waiting for a breakthrough in that front, and the scientists have to struggle with it in the hope of achieving a breakthrough. But at the moment, it's not competitive commercially and so on. And regarding how to reduce cost, see, the basic, nobody is working on gray hydrogen anymore, because they can see that gray hydrogen will not compete with direct use of natural gas or liquid fuels today, and it will not compete with green hydrogen tomorrow. So commercial investment, to my knowledge, is not happening because of these reasons of producing hydrogen from, by cracking natural gas or from coal or something. And people are doing it mainly to learn things and be ready for tomorrow, when there will be so much of green electricity available, either nuclear or from solar, wind, etc., so that they will be converted to hydrogen for the purpose of transporting, or for the purpose of chemical feedstock, or for making steel and stuff like that. So therefore, cost, that there are no indications that it's going in that direction, because people are making hydrogen for 100 years. People are doing electrolysis for many years. So on the electrolysis front, new things are happening. But rest of it, storage, transport, handling gas, making it liquid, making it denser, making it more pressure, these are traditional stuff, but there are strong engineering challenges, so that remains safe and economical. And the economy of scale people are getting. That's the way it is. And if I can find out, I or anybody can find out a easy or cheaper way of producing hydrogen, I don't think we'll get time to address to the INAE. We'll be counting money only all the time.
Okay, I think there is another question from Ram Kumar Singh. Ram Kumar, can you ask the question? Ram Kumar, can you unmute yourself? Or should I read the question?
Yeah, you can read the question. I was not able to speak because it was muted.
Okay, so his question is, can you please explain in terms of economics the green, gray and blue hydrogen that will influence policies in future? That is the first question. And then the second question is about hydrogen transportation in future. Will it be through pipelines or through carriers to make it user friendly?
Sir, my understanding is, first let me define what is green hydrogen. Green hydrogen has zero or near zero carbon footprint. That means if you are using green electricity from nuclear, wind, solar, hydro, that kind of sources, which has zero carbon footprint, with that you go for water electrolysis, and there are many technologies in that, and they are actually growing. At the moment, it's rather youth for the electrolysis technology. That is only to make it more efficient, but all of it is green. So that's green hydrogen produced by green electricity. The greenness is in electricity and not so much in hydrogen, because electrolysis itself is a green process. But it becomes a gray hydrogen when it is made out of coal, out of fuel oil, out of natural gas. Only thing happens by using hydrogen in your car is that the pollution, instead of being made in city, in a place where there are a lot of concentration of people and a lot of economic activities happen, it does make some sense to shift the location of the pollution creation. So instead of the polluting car, or instead of the car polluting Chennai or Bangalore or Calcutta, Bhubaneswar, whatever, it pollutes something which is 100 kilometers or 500 kilometers away in the rural area or in the forest area or wherever the power plant is. That is gray hydrogen. Equal amount of pollution but made away from population centers. Then if you add additional equipment, Whatever carbon dioxide is produced in the power plant, after all, it's coming out from a chimney. And if you lead the chimney into some kind of a chemistry, and so that the carbon is captured, the word is carbon capture. If the carbon is captured, means immobilized, made into some carbonate rocks and kind of put into a disused mine, that means what happened? You actually produced gray hydrogen, but you didn't allow the carbon dioxide to escape into the atmosphere. Instead, you immobilized it and put into a place where it can do no harm to population. That is called blue hydrogen. That's happening today. And green, all three are happening today. Green hydrogen is less. Now, we are hopeful that with time, it is the green electricity will get more, government patronage and so on, and technologies are going to be a little simpler, and more of it will be used. And as you can understand, how much solar was there and how much is there today, how much wind was there and how much it is there today, huge difference. And all these countries are kind of committed to make most of their electricity from renewable sources, and that is how it will happen. And green hydrogen will compete with the battery for cars, buses, and many things. And a battery has other disposal problems, hydrogen has none. So although hydrogen might be electricity to energy conversion is a little difficult, may not be so favorable, or changing and charging a battery versus charging hydrogen fuel could be different stories. But the disposal of hydrogen is far more benign, absolutely benign, compared to that of the lithium-ion battery, and that is where it is winning at the moment. Sir, what was your second question?
Yeah, this
Second question was about the containers. Transportation. Will the
hydrogen.
transportation be through the pipes or?
Yes, sir. Yes, sir. So obviously, all modes should be done depending upon the scale. So definitely a time when hydrogen would be ruling the world, that means when it will be true hydrogen economy, the consumption of hydrogen would be so high that pipelines would be economical. There is a large capital expenditure, but operating expenditures should be small and will be available. In the same way we are doing with the natural gas. But till such time that such a high level hydrogen consumption actually happens, it has to be with liquid tankers or with these high pressure containers, or converted to things like ammonia or methyl alcohol. uh, so so this ammonia, methyl alcohol, there are probably a few others candidates. It's converted to either organic substance or ammonia in liquid form. They can be shipped from one place to another in a regular room temperature tankers, and then they can be reconverted to hydrogen and nitrogen and so on. That will all be happening. One thing which I have read during these days is there is a network of natural gas pipelines everywhere. I mean, everywhere in the sense all continents, somewhere more, somewhere less. Our country is also having a reasonable amount, and all these natural gas pipelines can be used for hydrogen transport without any serious alteration. Pipes should be same, maybe instruments have to be changed, or maybe blower pressure drops would be different. So a couple of additional pumping stations will be required, but the entire underground infrastructure is usable with the green hydrogen, and that's bound to happen as hydrogen comes in bigger quantities. It will use the natural gas pipelines and displace natural gas from that locality.
Thank you very much.
Okay, so if there are no more questions, are there any more questions? I can't see anything in the chat box. So if there are no more questions,
Vivek Kashyap is asking something.
Vivek Kashyap already asked, right?
Okay.
Yes, sir. I do have one more question, if you permit, sir.
Okay, go ahead.
Yeah, thank you. Thank you so much for permitting me, actually. I was just curious, what would be the byproduct in general case if we burn, no, not burn, but if we transfer the hydrogen and oxygen fuel to the fuel cell and then converting it to the electrical energy. This is the general thing happens. It converts into the byproduct as water. But what if we directly burn this hydrogen and oxygen fuel? So what would be its byproduct, sir? Will it still be H2O, or it would be something else? Yeah.
Okay, my understanding is this. Fuel cell is much more benign, but suppose we put it to a IC engine and burn hydrogen in the IC engine with air. See, with oxygen there would be only H2O, and there is virtually no chemistry other than that. But it will not happen with oxygen, it is always hydrogen with air. Then there would be nitrogen. Because of the high temperature, NOx is produced, nitrogen oxides are actually produced. So if you think that in a internal combustion engine hydrogen combustion is 100% benign, that is not true, but some amount of nitric oxide, NO2, N2O, whatever, a combination, what we call NOx, is actually produced, but the quantity is much less. See, all those things which have carbon will not happen with the absence of carbon based organic fuels. There are carbon dioxide, carbon monoxide, or there is also contamination of sulfur, phosphorus, all that. None of them would be there, but nitrogen, because of the high temperature, NOx emission would be there. Then what they say, with the today's electronics, they could alter the spark timing or whatever, the very fine tune the IC engine settings, so that the NOx emission is minimized and it's far below what we are getting with petrol. With the diesel there is no comparison, because diesel is absolutely hopeless in terms of pollution production.
Thank you, sir. Thank you so much for answering this question. Yeah.
Okay, so I think with that we'll close the discussion today. And on behalf of INAE Chennai chapter, it's my pleasure and privilege to present the vote of thanks. So first of all, I would like to thank Professor Sunil Sarangi for agreeing to give a lecture. And it was a very informative and interesting lecture. I'm sure the participants have enjoyed it to the maximum extent. And I would also like to thank the INAE headquarters, particularly Lieutenant Colonel Shobhit Rai, the President, Professor Indranil Manna, and of course the INAE digital team for making all the arrangements for the webinar possible. My thanks also go to Professor Narayanan and Professor Ashish Sen for coordinating with Professor Sarangi and making arrangements for the flyer and all those things. And finally, of course, I would like to thank the audience, the participants, for making it a very interactive session. Thank you all very much. And we hope to organize more such webinars in future on behalf of INAE Chennai chapter. Thank you.
Thank you, madam, and thank you, Professor Narayanan. And
so thank you very much for the lecture. It was very
everybody.
interesting.
Yeah. Thank you, sir. Thank you for a very nice talk, and hope to meet you sometime.
Sure, sir.